morning, everyone. I see some people waiting outside. I remember a situation from my country where people are in a bus station thinking which bus to take, and the driver is waiting for passengers to decide which room they're going to take, if they're going to come for the session or not.
We take the fastest bus.
The fastest? They will not know. They will not know till they come in. Okay, let's start. I think it's 9:46. I know the previous session got a little longer, but I want to be done by 10:20 so that you guys can go for the next session. Thank you, everyone, for coming here. My name is SK, and I'm going to talk about this topic today. Before I get into the topic, I want to tell you a story. You guys like stories in the morning? Yeah. In AI, and especially in the recommender systems, I strongly believe that you got to really think out of the box, and you also have a clear view, as clear as possible, about the future, what's going to happen in the tech world. And I'm going to actually do a little bit of a test of you guys, whether you can actually predict what's going to happen in the future or not. But to test your prediction skills, I'm not going to talk about really the future, but I'm going to take you back 25 years ago and then ask you to predict 20 years from now. So you already know what's happened in the past, but okay, are you ready? A long time ago, before I even get to my story, a professor told me, when you say, "Are you ready?" or if you say, "Good morning," if people are not enthusiastically responding, then maybe I think they're not really driven yet. So I'm going to start again. Are you ready?
Yes!
Okay, here you go. So imagine this is the year 1995, and you're all venture capitalists with lots and lots of money, and I'm pitching in 2 different products, and you have to tell me 25 years from now whether this product is going to be super successful or super failure. Okay? Both are some type of encyclopedias. First one, in 1995, Microsoft announced they're going to come out with a fantastic encyclopedia called Encarta. Bill Gates is actually pitching in his personal credibility. Microsoft, a super successful software company, with lots of money, will be hiring really smart and talented, with lots of salaries and bonuses, program managers who would actually manage the whole development of Encarta. They announced that they're going to be in CDs with lots of pictures and videos and sounds. They could not put the smell part of it. I'm sure they could have tried. But anyway. And the company was hiring project managers, and even the authors who will be writing the information for this encyclopedia were full of high credentials. And they are going to make it a for-profit product. And there's a lot of excitement in the industry that there's going to be a very, very good product coming out. Okay? This is product 1. Product 2, which did not even come for 2 or 3 years later, was started by an unknown non-profit organization, which they said, we are going to do it on the web. People with no credentials, anyone rather for that matter, can contribute for this encyclopedia. No highly paid programmers will be managing, or rather project managers, managing this project. They didn't have a clue how they're going to even make money in the process. They did not have money in the first place to even spend. Which one I'm talking about? Wikipedia. So if you are being pitched these 2 products, and let's say you have lots of money, living in Silicon Valley, I'm guessing you have lots of money. And if you are asked to invest your money with the awareness you had in 1995, which product you would have invested in? Many people, the CD one, Encarta. Of course, that's not the truth, because I think in 2010, Microsoft announced that they're going to discard the product, and now they're disappeared, whereas Encyclopedia has around 3 million articles just in English. They actually have around 150 to 200 languages, articles on so many different topics. People are actively contributing. People are actively using it for their information. So having a grip of what's going to happen in the future, I think, is difficult. And the reason for that is I think so many things are changing in the process. And recommendation engines is one such contributor for products that's going to make or break going forward, and you don't even know whether it's going to be a super successful product or not based on the information today. And AI and recommendation engines are really making that happen. So what I'm going to do is I'm going to talk about a few of the published information. I cannot talk about the recommendation engine we developed internally because I think a little bit of a IP. I may lose my job, but I will talk about published information, and I'll tell you these are the ones which actually inspired us in developing a real robust rec system in the company. I'm going to be making a couple of assumptions about you guys, that you all are aware of what machine learning and deep learning means, and you have heard terms like RNN and LSTMs and stuff. If not, raise your hands and maybe I'll try to explain as much as possible. But because the main focus of the topic today is about recommendation engines, I think I'll try to focus more on that. Sometimes any clarifications on the basic AI terminology, I'll be happy to jump into. With that, any questions quickly you guys want to go to? This is a quick information I wanted to share with you. This is the sort of a fundamental information, and then I'll get into the published information. You all know recommendation engines are those which will intelligently understand who you are and recommend what may be interesting for you, right? On a very, very high level. But every time you pick a product, let's say you are recommending the next news item, or the next app you want to download, or the next song you want to, or the next outfit you want to buy, the logic, some of the implementation logic may remain the same, but the business logic or even the architectural knowledge you've got to get is fundamentally different. And the reason for that is the laws that govern some of these products, let's say in a news world versus a product world versus let's say an app world or a song world or a video world, they're all different. And I'll talk about that when I talk about those papers too. And to make it even exciting, I picked up 4 or 5 published reports or papers on the most commonly seen recommendation engines you might have encountered till now. Give me a couple of names what you have of recommendation engines you think you have heard of. And I may have that already. Amazon, Netflix. YouTube. I have YouTube. I have Google Apps and what else? Any other? Spotify. I have a music recommend. I think app recommendation, but not really a music recommendation. But maybe I'll talk about by the end of the session. Hopefully, you'll get a little bit of understanding of what does it take to design a recommendation engine. And let's get into the fundamentals. Companies collect data about you when you use their services or products. And many times you give some feedback about, let's say, the book you bought, or the movie you watched, or the song you downloaded. Sometimes you don't give any feedback. Historically, until 2 or 3 years ago, before deep learning really got picked up, especially in the recommendation system engine world, explicit feedback was very important for companies. In the sense, if you give a feedback, they want to latch onto the feedback and then make assumptions about who you are and who you're not. But off late, for the last, I think, year and a half or 2 years, something called implicit feedback. They don't really care for your feedback anymore. Don't give any more feedback. We can figure out what your feedback is. For example, if you're watching a video or playing a song, if you've played the entire song, or if you've watched the video 20% of the time of the whole duration, or 30% of the time, whatever the threshold limit is, that means you liked it. That's why you're watching it. And hence, the companies get the feedback. Of course, the feedback is yes or no, like or dislike, no, on a scale of 1 to 5, 1 to 10. So explicit feedback versus implicit feedback. Off late is more of implicit feedback. You have a question?
If you don't mind, can I ask, what is the guiding principle behind the recommendation? Is it content-based, collaborative?
Yeah, good question. So I paid him to ask the question because my next topic was about talking about various collaborative filtering and content-based filtering. Historically, companies used to design a recommendation engines based on the content. When I say content, it could be just who you are, so they profile you as an individual, and then figure out what could be the recommendations you would be interested in. Or they would profile the item or the product or the service you're trying to use. Let's say someone is selling a book or an outfit or a movie, they will profile that movie and say, okay, if someone liked this, and if I find that someone and other people who are similar to that person, so I can recommend the same movie because the first person liked it. Of late, recommendation engines don't use content-based filtering because that's so one-sided. Collaborative filtering, which is a term used by him too, is a concept where they want to find out information about users and the items. In this case, item is a generic term, which could be your song or the news or whatever it is. And if you look at the table there, you have all users and all items being captured. And whenever you get an explicit feedback, you actually capture the feedback, and now you have a sparse matrix. But if you can use the same concept for even implicit feedback too, if you based on your own heuristics or business rules, you have the implicit feedback, and you actually have, but you still have a sparse matrix. So not every user gives feedback for every service or the product he or she takes, and hence it's a sparse matrix. And it's always difficult for companies to make sense out of this information. What is more complicated in this context is a term called cold start. If you have introduced a brand new product and no one has actually bought it yet, how would you recommend that product to person ABC? Because you don't even know what the product stands for. Maybe you have a little bit of understanding of it, but you just don't know how it works. Or let's say a person for the first time signed up as a member. Let's say you signed up for Netflix or Amazon for the first time. Company doesn't have a clue who you are. Cold start is an additional complexity in a recommendation engines, and I'll talk about some of those topics too. But in overall, cold start is also being, to a great extent, addressed by using collaborative filtering. So to summarize on this particular slide, you actually have a sparse matrix with users and the items, and you actually have the implicit information being captured, and you start running your machine learning and deep learning techniques on it to actually find out more and more information. And if I have to summarize the entire recommendation just into a couple of sentences, from the sparse matrix, what you're trying to do is you're actually profiling a user with a very limited information itself. So you're actually creating an embeddings vector of a user or of an item, even with a sparse matrix. And once you have that embeddings matrix, you can actually proactively start recommending items by doing an inner product of this. But these are inner product, embeddings matrix. These are all typical machine learning, deep learning terms. I'm guessing you already know of it. If not, we can talk about offline too. So here is a very, very basic question, a basic equation. You have RUI is the feedback of a user U for an item I, and then you subtract that with the embeddings vector of the user, XU, or the user, and YI, the embeddings vector of item, and you compute the loss, and that's the most fundamental driving equation whenever you develop your deep learning solutions for recommendation engines. So that's for explicit feedback, and you also have implicit feedback. Implicit feedback is sometimes you don't know how confident you are about the feedback. Like, remember I mentioned, to compute the implicit feedback, let's say you're a video company like a YouTube, and you say, okay, if you watched a 20-minute video for 5 minutes, that is 25% of the time, that means you'll kind of like it. Or let's say 50% of the time, 20 minutes video you watch for 10 minutes, and hence we would design that threshold as you like of the video. That is not all the time correct. What if the person actually is playing the video and left the monitor to do something else and the video is still playing and you actually miscalculate? What if there was some other reason why the video actually had to play? And you also have heard of stories where someone is, to increase the video feedback or the ratings or the count, you actually can write a script which is constantly going back and running the same video multiple times to actually get the ratings up. To avoid all of these, you actually have a factor called confidence number. That is the CUI, the confidence probability of the recommendation engines for that user, for that item, and then you actually compute it. Now let's jump immediately into the paper published. All the papers I'm referring to are given a link at the bottom of the slides. When I started presenting, when I started speaking to teams a long time ago, someone told me the best way of making a slide is try to make it as sparse as possible. Put a little information so that it'll look nice to see the slides. And I forgot that today when I was making it. No, I was just kidding. I want to give as much information as possible for you guys. You can actually, I may not be able to talk about all the information here, but if you have any questions, I'll be able to answer. And also, this will be a good exercise for you to lift your hands up and take a picture of each slide too, because it's 9:40 in the morning. I don't know if you had coffee or not, but sometimes the topics could be boring enough to make you fall asleep. So.
One quick question. How does the data look like? I mean, input, like, is it it's a vector, I suppose, right? Like in case of image, it's like a pixel, right? So what?
Here the vector is the data would be, let's say, if you're talking about Google Play app download, it would be the type of customer, the gender, the age, geography, how many types of downloads, how many, what type of device. This is sometimes could be categorical data, sometimes could be continuous data, which would be, I'm getting into the details of machine learning here, but it's more of the information what the company thinks is relevant. Now, this paper was published, I think, in 2016. I think in the last, they're not published any more updates yet, but I'm sure they're working on updates on the product itself. So in 2016, they figured out they need some of this information. For example, age, they thought would be an interesting factor for profiling a customer. The number of apps installed, number of the engagement information, and how many times the person actually went back to the Google app, maybe even to give a feedback. User demographies, and such information about gender and age and location, and some of the other information too. All of this information, in 2016 they captured, but now they may be capturing more information. But what would be the super list of all the data they're collecting? I would not know. I don't think they would even reveal it also, what they're collecting. But it could be all type of information. I think what you're referring to in terms of image is a pixel. That is when you're doing an image processing per se. Here we're talking about making recommendation engines based on more of a numeric data that's coming in from the customers. So what is the uniqueness in an app situation? And I want to highlight that in the context of, let's say, 2 years ago, 3 years ago, or in a non-machine learning, non-deep learning solution, if you find, you can actually start profiling all the customers, let's say, of the same age, or same gender, or same geography, or same type of education background. You can say, okay, if you're a student, and if another student has already bought this app, maybe you want to buy it too, and hence you can. That would be a very simple, naive implementation of a recommendation engine, but that's not the case all the time. In an app situation, here is the additional complexity. Let's say you download a music app today. What's the probability of you downloading another type of a music app onto your device? Almost zero. Maybe if there is another something going up in popularity, but the probability drops immediately. Unlike, let's say you download a song and another song of the same type, you may download it because you kind of like that type of songs and hence download it. But app, once you download one type of app, let's say music or a running type of app, or I don't know, any social media type of app, the probability of you downloading all the similar apps would be very less. But the further additional complexity is, what would be the app that goes with this app within your profile? Let's say you downloaded a music app today. Would you be interested in a running app which will go together, provided you are a person who are into running and stuff? But let's say you are not into that. You download a music app, maybe you can download a dance type of an app which will go in conjunction because you are into dance. How would you make these predictions and then make a recommendation would be the difficult part in an app development system. Once that clarification is done, this is a straightforward deep neural network implementation for, actually there are two types of models in this case. They're actually using something called a wide model and a deep model. In a traditional recommendation engine, people just use a linear regression just to predict, okay, based on the user information, the item information, we can make prediction using linear regression. This is quite useful provided products are all similar and people are all similar to each other. And you start getting information about the users and the products. But when you want to get newer apps being installed into uploaded into the store, and if you want the model to be able to predict what would be the next app that could be recommended to this person, then you actually use a deep learning method. So there is here they use something called wide and a deep model. The wide is the model which uses pure linear regression. So you get just the cross product of the user information and the item information, do the multiplication, and then find out the vectors, resulting vectors, and find the nearest vector that goes with that and recommend those as the next app the person can download. But that, they said, was, if you look at the metrics on the top, just the wide model alone or just the deep model alone was not as effective when they combined that into end-to-end model. Not an ensemble, but an end-to-end model, and the model actually picked up faster, because I'm sure you know the difference between an ensemble versus an end-to-end model of various topics. Because if it's an ensemble, each one has to be trained with the full data, with all the information, takes more compute time, and then you're actually heuristically doing the average of all the outcomes of each of the model. Whereas an end-to-end model, sometimes it can actually complement the weakness of one model with the strength of the other model, and hence the convergence will be faster and less compute time, less data, and all of this stuff too. So in this Google Play, what they're using is in the deep model, they're using a deep neural network, which actually converts all the relevant features, in this case the information they're taking, into embeddings, and they actually run the embeddings separately to compute the embeddings. And after that, they just concatenate all of these input features into a longer vector. And I think that typically the dimensions are around 1,200 dimensions vector. And after that, it's just a pure neural network processing and running a softmax at the end of it to make a prediction. That's a very, very simple model. After the moment you figure out the user embeddings and the moment you actually concatenate, horizontal concatenation, then it's just a pure neural network, and the complete information about the hyperparameters, the number of layers, etc., are in the paper. But on a top level, that's information on how to develop a recommendation engines for an app-based system. And I mentioned to you earlier, the complexity is if you download one type of an app, the probability of you downloading the same app or similar type of app is quite less.
Can I ask, is it a multi-model system now?
These are, they're using two different models at this point of time. That's what I'm understanding when you say multi-model.
Yeah. I mean, two different networks.
No, this one is this is a pure machine learning model. The cross product multiplication is just the user information and the item information. They do a cross product of that. That's not a neural network, but the neural network is the wide model. The deep model, and the wide model is just a cross. So you actually have one DL model and one machine learning model together. They are trained end to end.
Yeah, because sometimes if you have images, you have one network. For text, you have another network. Then you combine.
Yeah, so that's what I meant to say when I mentioned the difference between an ensemble and an end-to-end model. If the example you gave, if you actually do an end-to-end model, you actually can have the same model or other different layers of the model picking up information from, let's say, textual information, image information, numerical information, and eventually in a fully connected layer, maybe they can process it together and do a softmax on that. You can do that way, or you can just have one exclusive model for just the text processing and then get the outcome of it, softmax maybe, and you actually have another model with image processing. But it all depends upon which one is providing better results. At this point of time, even many of the AI experts, there's a little bit of a hit and trial all the time going, because they just don't know exactly what's the best architecture to come out with, whether it's going to be an ensemble or end-to-end. And I know it's a good question. I don't know if you actually have started reading the technical papers on AI. And 2-3 years ago, when I was into the AI world, I was not that expert, I did not understand much. I was reading the technical papers, and it was very difficult to understand a paper. And I don't know how much of you guys can understand the paper today, but my opinion about a technical paper, including this paper I just mentioned here, is papers are written not to educate you guys. Papers are written just to show how smart the authors are. And hence, if you just read the paper, I think it's so difficult to understand completely what they're trying to solve, unless you're already an expert in the whole world. And when you see a published paper, what you don't see is the failed experiments they had. You would see just the successful experiment, and hence they published that. There's not much of effort being spent today to actually capture all the failed situations, because we don't know what will fail. And hence, if you are doing a research on a similar area and on a similar topic even, you will end up repeating those failures to yourself in your lab experiment, and hence, I'm guessing if someone is going to watch, I'm recording myself and I'm going to put it on YouTube. If someone is going to watch my video later on from the academic circles, I would actually want to tell them that you should also have, if not on a paper, but somewhere publish all the failed experiments too, because people actually then start avoiding it, they can avoid repeating those experiments.
Maybe an addendum at the end of the
Wherever, yeah. See, papers, addendum is another complicated. I think paper already 25 pages, 50 pages. Papers are coming in, and if I have to read even the addendum, it's going to be even more complicated. But they can put it on the website somewhere on what it is. Okay, how do you design a recommendation engine that recommends to you the news items? Now, what are the additional complexities in a news recommendation engine compared to a regular recommendation engine? Regular recommendation engine is based on your user information and item information. You can predict what the person likes. But in news, there are a couple of complications. One, if you just compare the topic titles, it is always difficult. They may have different words being used for the same topic. Let's say if you have CNN and BBC and let's say Fox News, and they're publishing information about the same traffic accident, they may use different words. And you just cannot do a basic word match. But at the same time, some of these news stories are evolving stories. Let's say you had an accident in the morning and they published immediately something for within the first 1 hour, but 3 hours later they actually update further, and then maybe a day later they will further update the information. If the model thinks, oh, I've already seen this, I've already recommended this, and I should not recommend anymore, but you're actually letting the user not to see the latest news item too. So sometimes you recommend, the recommendation engine has to actually be a little more intelligent to figure out, okay, even though I've recommended the same news item, but this is an evolving story, and hence I have to pick something different. Next, just because a news item was extremely popular yesterday, I cannot recommend that popular item today. In this paper, what they picked, the assumption they make is every 24 hours, they would flush out the entire news articles they have and pick the latest news articles to analyze, prepare the list, and then start recommending. So that's the complication of a news recommendation engine. Now, this paper was specifically written by the Yahoo Japan team, this I think published in 2017, and especially for mobile devices on a cell phone. If you look into the form factor of the screen, the top is the first view, and then you actually have the personalized view on the same one screen. Even if your model is extremely intelligent to figure out what type of news I should recommend to this user, you got to be so creative. The top 2 or 3 items you're recommending has to be so on the dot, because no one is going to scroll down the screen if the top 3 you're recommending are really bad items. They'll just say, oh, what the heck, you don't even get what I'm talking about. So one is not just identifying the candidate news articles, identifying the priority and ranking of it is going to be extremely complicated too. I'm actually going to talk about the same approach, a similar approach taken by YouTube guys in my next slide. But in this case, Yahoo News published this paper on how to identify. Now, couple of basic things in a news article. How do I know article number 1 and article number 2 are the same and article number 3 is not the same one? You just can't do a word match, because if they've been written by 2 different news reporters or different news agencies, they may not have word matching. And that's actually a bad idea too, people figured out. There used to be 4 or 5 years ago, there's a technique called TF-IDF, term frequency and independent document frequency, and that doesn't work anymore. You have to use deep neural networks. They converted each article into word embeddings, and they do a similarity index between 2, let's say if you pick 3 articles, between 1 and 2 and 1 and 3, they would do a distance computation between these 2 vectors, these 2 vectors. And whichever is higher than certain threshold, then they would know these are 2 different articles, and hence I can show them if they happen to be within the profile of the user. If 2 articles, even though they seem to be matching for the user profile, but they're very close to each other in terms of the vectors, they won't recommend both, they just recommend only one. So if you look into the encoding of the triplets of articles, let me step back. The whole process is first human in the loop. Editors do categorize the articles coming in from the entire world. They have so many news agencies publishing information, they actually categorize it into, let's say, economics or politics, and if it's a geo-specific, then talk about geo too. On top, they also have information given by the users about their preferences. When you actually open an account, let's say on Yahoo News or anywhere, they would ask you, okay, what type of news you like, and you actually would have picked, you would have clicked 3 or 4 items, and then based on that, they actually further shortlist the number of articles they can recommend to you. On those articles, they want to find out, pick any 3, and then find out which ones are very close to each other, which are not very close to each other. So they do a basic encoder decoder, which is here you may be using a pure encoder decoder, or could be an auto encoder. These are some of the technical terms. If you don't know what it is, I'll explain auto encoder in a couple of minutes, but you convert the articles into word embeddings and do a cosine similarity of these 3 vectors. Whichever 2 pair of articles cosine similarity is higher than certain threshold, they would say, okay, these 2 are dissimilar articles, and hence I could show them.
Sorry. So I think that you're talking about kind of similarity, but basically you try to measure kind of the mean of your bias or your view, but do you capture the kind of the spread of kind of your view? I mean, if you have kind of wider kind of interest versus some people have more narrow interest, their mean could be same, but their kind of the spread could be quite different. So how you capture that?
So then I need to go back to the very start of the whole discussion. When the news article is coming in, based on the feedback given by the user when the person was opening up an account, and what seems to be popular today, because you actually know, being an editor yourself, you know something is popular. Let's say the elections of country ABC, or an accident or a terrorist act. So they have the popular item. So the intersection of those, the user preferences mentioned and the popular items, you actually have a narrower candidates you can pick. So you actually, the news population is reduced. On top of that, you actually have a user profile already based on your browsing history. AU at time t is the browsing history of a user U at timestamp t. So they actually have a little bit of a historic information. So if you have used the model earlier, so then they already know what type of person you are. And if you are doing it for the first time, then it's a kind of a cold start where they will only rely on what is popular today and based on your preferences given. Okay? Let's make an assumption that you have used the model for some time, and hence the model knows a little bit about you. So the model knows about you, you have given your preferences, and you have the popular or trending topics. Based on all these 3, you make a shorter list of items that you want to prefer. In that shorter list, even there is a spectacular new invention on, let's say, a new planet, but that is not within the profile or the preferences or the trending topics, and if it doesn't score in the top, let's say 50 or 100, it will not be shown. So the wide range of possibilities, it will be narrowed down artificially. Artificially, when I say artificially, it means based on these 3 requirements, as I mentioned earlier, but they have to limit, because you also have the response time requirements too. You can't take 5 seconds, 10 seconds to load things. You've got to take a sub-second response. So I don't know how much is the target they have. Maybe I'm guessing candidates could be, let's say, 1,000 articles they would pick, maybe 500 articles they could pick, and then they can do a quick analysis, because you're talking about millions of users trying to access a mobile device. You also have to be aware of the computing power of your mobile device, plus even the network capability, all of that stuff too.
I think they make use of the very simple way. The simplest way is you take the browsing history of most recently 10 news stations.
Yeah. You're right. The problem with the browsing history is...
I mean, for this question.
Oh, okay. So you're trying to answer his question. So maybe you guys can take it out offline then. Yeah. So that's what it is. So they do mention, they do have a little bit of an artificial limit on how wide range topics can be. How do they capture the user profile? Now, recommendation engines of late, there's a new topic in the recommendation engine world called session awareness. Let's say 1 month ago, you were interested in, pick a singer, famous singer, Britney Spears maybe, is she still famous? I don't know. Let's say you were listening to her songs, but now you have moved on to a different singer, you want to listen to her songs or his songs, but the model cannot take, oh, you heard earlier Britney Spears too, so I'm actually going to combine a few of that, few of this. But you don't want the model to think about that. So off late, session awareness. Let's say you have logged into the model right now, or logged into the model just today, or just this week, not previous week, or just this month, not the previous month, just this year, not the previous year. So the session definition can be varying for different models, but companies are trying to focus on the feedback they're getting. Or if they have to consider for the entire history of you, they would give more importance to the recent searches and recent feedback, what you're doing versus the historical feedback. I'm running out of time. So let me go to YouTube and then I'll stop, and if you have any questions, and I'll do you know every minute 400 hours of video is being uploaded to YouTube? Of course, it's impossible to watch or even find the relevant ones. So YouTube published in, I think, 2016 or 17 this paper where they would do two different models. One is a candidate generation, which from the millions of records, I think they bring it down to, I think, 500 records, 500 videos. And within the 500 videos, they would actually do a ranking part of it. And they also implemented the session awareness concept. For example, if you have been searching for certain keywords off late, those videos had given more importance to the previous ones, but still, they would still remember. Let's say you heard Britney Spears once upon a time, so they do know that you like that type of songs, and they would still show, unlike the news recommendation engine, where even though something was very popular yesterday or 2 days ago, 1 week ago, they will not show that any more information, even though you liked it so much, that's not relevant anymore today. So that's the difference between the news and the YouTube in terms of the videos. Once those conceptual informations are clear, rest all is a pure neural network where you identify the various features, in this case typically the user profile and the video embeddings. Video embeddings is how long the video is, what topic the video was, where it was located, what is the focus of the topic. These are some of the features you extract from the videos and create user embeddings and run a neural network. As I mentioned earlier to you, once you've got the features figured out, doing a deep neural network is more of a, not really trivial, but almost a trivial topic. I'll stop off at that. It's 10:22. If you have any questions, I'll be more than happy to talk. If someone wants to leave for the other session, I think you're more than welcome to leave too.
Thank you.
Thanks.
So sounds like this. So anybody try to use the kind of reinforcement learning on this class? I think it looks like a good topic in that way.
I have not seen papers till now using reinforcement learning for recommendation engines. Right now, people are just using the basic neural networks, maybe ensembles or different types of networks, but I have not seen yet reinforcement learning.
Is it because it's potentially risky?
No, I think the reinforcement learning, I think some companies are using reinforcement learning to augment the data, so you can do for the collaborative filtering, you have the sparse matrix, maybe they can do the reinforcement learning to actually create, you have the GANs maybe being used to actually augment the data. But till now, I think people are just taking, if you have the input features, they can use a simple neural network to run and then identify what the next recommendation engine is. I think till now. Reinforcement learning, I've not seen. Could be, but yeah, I don't know.
Okay.
Have you seen any applications of things like topic modeling or unsupervised models in recommendation systems?
Yeah, I have seen, but that's an older technology now. Topic modeling is one of the oldest ones. Like in the news recommendation, that used to be the most popular one. Let's say you write a news article and then you publish it about, let's say, a company ABC which is producing this product had a major fire accident today. That news article can be categorized as an accident topic, or it could be a technology topic or a manufacturing topic, whatever it is. So the topic modeling, you run a topic model, look at the whole data, and as I mentioned, TF-IDF was the earlier technique, but now people use other techniques. Just based on the TF-IDF, they can tell you which topics this will fall into. Maybe one, more than one. And then once the topic modeling is done, and let's say you as a user said, oh, I like all the technology, this may find its place there. If it's a technology and crime, because this is in both areas, it will come up top on the higher hierarchy. But not anymore. Topic modeling is an older technology now.
So I read that one of the benefit of deep learning is you don't have to do any like feature engineering.
Uh-huh.
I mean, without you finding out which features are important. But you said still
Yeah.
for YouTube they're doing that, or for
Yes.
Play, Google Play.
You're right, and I'm right too. And
No,
and
no,
the re-
I'm just like
no, that's fine. I understand.
Yes, yeah.
The reason for that is compared to machine learning, where you've got to do lots of feature engineering, otherwise model is going to really do wrong predictions. Deep learning model can actually figure out some of these things in its own way, but does not mean that you can give all the whole data in the world and then let the model figure out, because then there's a computational cost I think is involved, the accuracy, and so many other features too. So from that sense, as a human being, you can just say intuitively, oh, for a